Section 7.3 is titled Multivariable Linear Systems. In this section we're going to do a lot of what we did in section 7.1 when we solved 2 by 2 linear systems in the way of doing some substitution and elimination method. We're also going to tie in to this section some of what we learned in 7.2 dealing with inverse matrices and show how we can use those to solve systems of equations. Alright, this first example is one where we have 3 equations and we have 3 variables, an x, a y, and a z. We're trying to find the x, the y, and the z. It's not really that standard of a problem because typically all 3 equations will have all 3 variables, but it is a good kind of warm-up problem to the overall process and feel of what we're going to be doing. So I look at the bottom equation and I notice that it is ready to solve for the z already. If I take that equation, negative 4z equals negative 12, we divide by negative 4, we get that z equals 3. Okay, so it's easy to find the z in that equation, so we've done that. Well, now if we go up one level to the middle equation, where it says 2y plus 3z equals 3, we can write in now 2y plus 3 times the z, which is 3, equals 3. We can solve this one for y. So that's 2y plus 9 equals 3. So we subtract 9, we get 2y equals negative 6. Divide by 2, we get y equals negative 3. We got that one. So now we have 2 variables solved for. We need the third. The top equation has got all 3 variables in it. We can put in the values for the 2 variables that we know. So the top equation is x plus 4y, and y is negative 3, plus 3z, and z is 3, and that equals negative 2. So we have x minus 12 plus 9 equals negative 2. That's x minus 3 equals negative 2. And if I add the 3, we get x equals 1. Okay, so our goal was to find the x, the y, and the z, and we have now done that. We have the x, the y, and the z. We typically write the solution as an ordered triple: x, comma, y, comma, z. Alright, this next problem that we're asked to solve the system is a more kind of standard example where all 3 equations have all 3 variables in them. So we need to solve, again, same thing, we need to solve for the x, the y, and the z, but how do we go about this when it's not set up to just go ahead and do that at the outset like the last problem? And the answer is that we do some elimination method to the system first. I'm going to try and cancel one of the variables, either the x's, the y's, or the z's from the problem. And it doesn't matter which one I choose or you choose, we can choose different variables, and in the end we should all work out to the same solution. What I'm going to do in scanning this, and knowing that I need positive and negative numbers to add to 0, that sort of thing, I'm going to choose the y's. I think I can easily deal with the y's. I think I can cause a lot of those to cancel out. So I'm going to take, begin with the top 2 equations. Or maybe the top one and the bottom one actually. So the top equation is 5x minus 2y plus 2z equals 2. Now I'm going to take the bottom equation also, and I'm going to take this bottom equation times 2. So giving me 4x plus 2y minus 8z equals negative 14. And what I've created is an opportunity to cancel out the y's in doing that. So we have now 9x minus 6z equals negative 12. And we're going to just kind of pause on that for right now. So I've canceled out the y's once. I need to cancel out the y's again, okay, a second time. So I'm going to take this equation. I'm going to take x minus 3y plus 5z equals 7. And I'm going to take the bottom equation again, but this time I'm going to take it times 3, giving me 6x plus 3y minus 12z equals negative 21. And again, the y's cancel out. We get 7x minus 7z equals negative 14. Okay, so you can see what my goal was. My goal was to get one variable canceled twice, because the result is that I have two equations now that have the same two variables. I'm going to even simplify these equations. This equation is all divisible by 3. This is the same as 3x minus 2z equals negative 4. This is all divisible by 7, so this is the same as x minus z equals negative 2. Alright, well now I'm going to pull these equations together. Okay? I'm going to take this equation and this equation together. Okay, so that's the first one. I'm going to take this equation times maybe a negative 2. Looking at the z's, that would give me negative 2x plus 2z equals 4. Here the z's cancel out, we get that x equals 0. And after all that work, we found out what one of the variables equals. Okay? Well, so now we're going to use that and we're going to start substituting our way backwards through the problem. If x equals 0, then we could place it over here, and we could say that 0 minus z equals negative 2, so negative z equals negative 2, so z equals positive 2. Okay, so now we've got x, we have z. All that's left is to find the y. I'm going to take, and I'll draw a line here to show, I'm going to take this bottom equation. So I'm going to put 2 times 0 plus y minus 4 times the z equals negative 7. I'm going to solve that for the y. This, of course, goes away. This, I add 8 to both sides. And we get y equals 1. So now I have x, I have y, I have z, I have the problem solved. My solution 0, 1, 2. Okay, so there you have kind of the amount of work that's generally required in maybe a standard 3x3 linear system. Again, we start with 3x3 system. What I did is I reduced it to 2 equations and 2 variables that I then brought together and did more elimination to cancel to get a variable solved for. And once I have one variable solved for, we work our way back through the system to get all the variables solved for. Alright, the next 2 slides, what I want to look at is a couple of problems that have unique solutions. Not the standard you're going to find an x, a y, and a z sort of answer. But this first one is one that has no solution. And so I want to kind of show that process and what that might look like. Now I begin this problem, again I scan over the system and I try and decide which is going to be easiest to cancel, the x's, the y's, and the z's. And you might notice, like I do, that the x's are set up to cancel in these top 2 equations. If I add these x's together, they add to 0. So I add the y's together, I get negative y. I add the z's together, I get negative 4z. I add the 4 and the 3 together, I get 7. So I'm going to save that equation for now, just kind of hit pause on that one, and I'll come back to it later. Well, since I've canceled out the x's, I need to cancel out the x's again. And to do that, I find it easiest to use the bottom 2 equations here. The bottom equation's got that 5x so the middle equation would have to have a negative 5x. And if I take it times 5, I'm going to get negative 5x. But I take the whole thing times 5, so that gives 10y minus 25z equals 15. So the x's cancel, we end up with negative 3y and then minus 12z equals 23. Okay, so now I'm going to pull these two equations together. I'll pull this equation. So it is negative 3y minus 12z equals 23. I'm going to pull this one down here too. I'm thinking cancel the y's or cancel the z's. Well, in this case, I take it times negative 3 to make it become positive 3y. It just so happens to also become positive 12z equals negative 21. And so what happens is that the y's cancel, but also the z's cancel, and so I get 0. And on this side, I get 2. And that's an illustration of a contradiction. 0 does not equal 2. And once I have that happen, I can say that this system has no solution. Okay. Sometimes all the variables drop out very early in the process. Sometimes they don't drop out until kind of later in the process like this. But at some point, if all the variables end up dropping out through elimination and we've got this contradiction that results, then the answer is no solution. Okay, this next system of equations is one that's going to have infinitely many solutions. So I want to show how that happens and how we solve one like this. So I begin by, again, scanning over the system and trying to decide which do I want to try and eliminate, the x's, the y's, and or the z's. And you probably notice, like I do, that in the top and bottom equation, the x's would cancel. But in the top and middle equation, the y's would cancel. So I've got two kind of easy options to go with, and neither is going to be more right than the other. So it's really kind of up to you how you'd want to go ahead and do this. I'm going to go ahead and just deal with the x's. So I'm going to take this equation and this equation. The x's cancel out, so I'm just going to add them as I go here. 3y and 6y make 9y. 10z and negative 4z make 6z. And 2 and 7 make 9. If I reduce this, I can divide this by 3. This makes 3y plus 2z equals 3. So we're going to just hit pause on that. We're going to save it. We'll come back to it later. Now, since I've canceled out x's, I have to do that again. And so I'm going to take the bottom two equations. The middle equation is 2x minus 3y plus 14z equals negative 5. The bottom equation to cancel the x would have to get times by 2. So that would make negative 2x plus 12y. Looks like minus 8z equals 14. X's cancel. We get 9y plus 6z equals 9. And if I divide that one by 3 to reduce it, I get 3y plus 2z equals 3. Now you might notice, like I do at this point, that my two reduced equations that I have are identical. If I were to put these two equations together, maybe I take this one as it is, 3y plus 2y equals 3. I take this one times negative 1, giving me negative 3y minus 2, that should be a z, equals negative 3. Y's cancel, z's cancel, 3's cancel, we get 0 equals 0. Whenever we get this situation, so it's not a contradiction, this is an example of infinitely many solutions. Now, we're going to go a little further in the process of solving this than we do in an Algebra 1 or Algebra 2 course. We're going to find the form of the answers of these infinitely many solutions. And so let's show that, how we do that maybe on the next slide. I'm just going to use a blank piece of paper here, but keep this problem handy because we're going to be referencing this. Alright, so what I need to do is I need one of the variables solved for so I can substitute back into the problem. And since all the variables cancel out, we're just going to pick one. Typically we pick z, so I'm going to let z equal a. Okay, so there we go. I've got a solution for z. Okay, it's not a numerical solution, but it's a solution nonetheless. Now I'm going to pick, well, they're the same equation. I'm going to take that two variable equation, that 3y plus 2z equals 3 equation, and I'm going to substitute my answer for z in for z. So I have 3y plus 2a equals 3. Let's solve this for y. So I bring the 2a over, I get 3y equals 3 minus 2a. I divide by 3, and I get y equals 1 minus 2/3 a. Okay, so now I have y solved for. So I have z solved for, I have y solved for, now I need x solved for. To solve for x, I'm going to use the top equation of the original system. That top equation was x plus 3y, and y is 1 minus 2/3 a, plus 10z, and z is a, equals 2. Okay, so I'm solving this for x. I have x plus 3 minus 2a plus 10a equals 2. I just distributed here. So then I'm going to subtract the 3. So I've got x plus 8a equals negative 1. I'm going to subtract the 8a over here, so I have x equals negative 1 minus 8a. Okay, so I've got an x, I've got a y, I've got a z, I've got this system of equations solved for. Solution is negative 1 minus 8a, comma 1 minus 2/3 a, comma a. Okay, so what I have now is the form of my infinitely many solutions. So now that if a was any number, like for example, if a was equal to 1, well then that means 1 is the z. If a was 1 here, I'd have negative 1 minus 8, I'd have negative 9. And if a was 1 here, I'd have 1 minus 2/3, I'd have 1/3. This right here is a solution. But there are lots of solutions because a could be any number, and if a was any number we wanted it to be, then I could find the x and the y to go with that any number. So this is just a possible solution, one of many, infinitely many solutions, but all the solutions take this particular form right here. So with any infinitely many solution answered problems, we're trying to go all the way to here. And so again, we typically start with z equal to a, and then we kind of plug that in and solve in terms of a for all the variables. Okay, finally in this section, what I'd like to do is show you how to solve systems of equations using inverse matrices. The first thing we need to do is we need to translate this, or we need to rewrite this system of equations as a matrix equation. So the matrix equation looks like this. We take the coefficients of the x's and the y's times the variables x, y, and that equals the solutions to the system 9, 10. Okay. Now what we're going to do is multiply to both sides. And I'm going to just rewrite this so I can slip this in on both sides, but okay. what I'm going to do is multiply this side by the inverse matrix of the coefficients. So that's indicating inverse. And so I'm going to multiply by the inverse on this side as well. Okay, so why would I do that? What does that actually accomplish? Well, we should know that, for example, okay, kind of like scratch work example. Let me kind of see if I can fit it in up here. For example, any number, say 5 times its multiplicative inverse, 1/5, in this example is 1. Or if I were to take 8 times its multiplicative inverse, 1/8, I get 1. Right? Or if I take 2/3 times its multiplicative inverse, 3/2, we get 1. Okay, like we know that. Okay, so apply that here. If I take this matrix times its inverse matrix, what happens is they cancel each other out, and the result is just the identity matrix, which is 1 in matrix numerals, but it's 1 times this, and 1 times this is just itself. It's just going to be the xy. So what I need to do is multiply this inverse matrix times this matrix here. Now we can do this by hand certainly, but we've got the power of the graphing calculator that has these matrix capabilities. So I'm going to do this problem on the graphing calculator. Okay, so I begin by going into matrix. I'm going to edit matrix A to be the 2 by 2 coefficients. Okay, so it was 2, -3, 3, -5. There it is typed in. Now I'm going to go back to matrix. I'm going to edit matrix B to be the 2 by 1 solutions. 9, 10. I'm quitting and I'm getting out of that. So I have typed this matrix as A, this matrix here as B. I want to take A inverse times B, and the calculator will do the inverse and the product all at the same time and will get my answer for me. So that would look like this. I'm going to need matrix A, the inverse button, times matrix B. So the answer is 15, 7. Now, if you just simply match them up, x matches with 15, y matches with 7. The solution to this system, 15, 7. And so there's an alternative way to solve this problem that doesn't require substitution or elimination method to do it. Alright, the last problem here, I'm going to do the same way with the inverse matrices. I'm just going to skip a step and get right to x, y, z is going to be equal to the inverse of the coefficients. The coefficients are 1, -5, 3, 2, -3, -1, -2, 2, 1. I want the inverse of that times the solutions, 2, 1, 12. And so x, y, z is equal to. Now it's just a matter of typing those two matrices the 3 by 3 and the 3 by 1 into the calculator and doing this one's inverse times this one. Okay, and so let me do that here and you can kind of see what that looks like. And I'm just going to do it in real time so you kind of get an idea of how long this takes. Okay, there's my 3 by 3. I do, as I type it in, I do just kind of double check and make sure that I didn't make any errors putting any numbers in. I'm going to edit matrix B. It's going to be a 3 by 1. It's bigger this time than the last example. Okay, I've double checked, the numbers look good. I need to tell the calculator to do A inverse times matrix B. Let's try changing to fractions. So I get negative 177 sevenths, negative 13, negative 88 sevenths. And typically whenever that happens, I'm going to go back into my matrices and just make sure that everything is typed in correct. I know I said I checked them, but I'm just going to check them again here real quick. 1, negative 5, 3, 2, negative 3, negative 1, negative 2, 2, and 1. So that one's typed in good, I know. I'm going to check what matrix B looked like. 2, 1, and 12. So everything's typed in good. So these are, in fact, my solutions. Negative 177 sevenths, negative 13, negative 88 sevenths. And that's finished.